through. Here we are. Here we are. No data. Excellent. Awesome. So we did take a L. We're not able to live stream on TikTok, but we can live stream on Twitch and YouTube. So the journey continues. We gotta just keep the ball rolling, stay consistent. I watched the last live stream that made it to YouTube, and I noticed that like if I'm listening to my headphones, I can hear it on like either side. So the goal right now, before I get started, is to make sure that we can hear it on both sides, and it's not just kind of stuck on, you know what I mean, like on one side of the ear for people that are listening with headphones. Because maybe people actually really can't hear me, and I haven't even noticed. So to the people that actually did pull up and say, "Hey, I can't hear you," dang, I feel you. Now I feel bad a little. Only a little because like y'all really were here to like come vibe with me. You were trying to sell me something. But hold on, let me see. Let me see. Hold on, let me see. Let me see. Yeah, 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 yeah. What are we gonna do next? Yeah. What are we gonna do next? Yeah. What are we gonna do next? 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 Yeah, it's kind of lower on that side. What are we gonna do next? Yeah, it's kind of lower on that side. What are we gonna do next? Yeah, it's kind of lower on that. What's going on? Hmm. What's going on? Hmm. What's going on? Yeah, wow, the echo's even better. What's yeah, wow, the echo's even better. What's yeah, wow, the echo's even better. Hmm. Hmm. What's the word? What's the word? Catch your vibe real quick. Catch your vibe real quick. Direct monitor. Catch your vibe real quick. Direct monitor. Catch your vibe real quick. Direct monitor. Direct monitor. But if I turn it off, I can hear it clearly. Direct monitor. But if I turn it off, I can hear it clearly. Nah, not really. Let me see if I turn up the monitor. Let's see what happens. Nah, not really. Let me see if I turn up the monitor. Let's see what happens. There's not much of a change at all. There's not much of a change at all. I thought it was just the headphones, but it's like even in like the recording, that's how it's coming out. Like even in like the recording, that's how it's coming out. Even in like the recording, that's how it's coming out. It doesn't make it easier that like it's echoing. It doesn't make it easier that like it's echoing. It doesn't make it easier that like it's echoing. It doesn't make it easier that it's echoing.
I have an impulsion for getting up in my own way. I wanna do right and kill everything in my own lane. I always way. I wanna do right and kill everything in my own lane. I always way. I wanna do right and kill everything in my own lane. I always way. I wanna do right and kill everything in my own lane.
So why is it that I can hear clearly on both headphones for clearly on both headphones for like the computer, but like when it comes to recording, I can't. For like the computer, but like when it comes to something that I'm doing wrong, I can't. For like the computer, but like when it comes something that I'm doing wrong, I can't. I thought it would be like making it a direct monitor. That would make it better. Making it a direct monitor. That would make it better. But I can't even hear it on this side. But I can't even hear it on this side. So let me make it dual. So let me make it dual. So dual. If you want to, I can order it. If you want to, I can order it. This is sincerely a conundrum for me, guys. But we're gonna keep on going because I do have company coming over. I do want to spend some time with my family, but I also want to stay committed to what I said I was gonna do. So I'm gonna read a quick section of engineering. Oh, my fault. You know what's going on right now? There's echo. Let me turn the echo off. Engineering. Oh, my fault. You know what's going on right now? There's echo. Let me turn the echo off. I feel bad because like if someone wants to come and watch my shit, the first 5 minutes they're just gonna hear an echo. That's a great way to keep people in the loop, I guess. But anyway, we're gonna keep on rolling. We're gonna keep on vibing, and in all of this excitement, I got hot. I'm going to get a fan or something. All right, fan is acquired. Wind is blowing at me. My baby's looking at me, laughing, saying what's up. And we are going to do what we said we're going to do. One of the 7 spiritual laws of success is have your word being impeccable. Make your word impeccable. So if you say you're gonna do something, do it. And watch what it does to your subconscious. Now you can say some grandiose thing, and your subconscious is sitting here like, oh man, this is actually gonna work. I believe in it. No, it's okay. Honestly, maybe I can just do this another time. Yeah, You sure? Okay. I appreciate you, baby.
You go off.
That's what I'm talking about, y'all. Like I didn't want to make it like a relationship thing, but yo, it's a community. Like I'm trying to do something and trying to get this done. And you know, this is a really secondary thing compared to family. So I was thinking about cutting it off just, to do that, but my girl came through and she said that she got him. So, it's working together and trying to get that, rolling. At least that's what I think. You know what I mean? Like I just got here, I'm 30 years old, first time being in a relationship this long. First time taking the steps of like marriage, you know what I mean? Engagement. That's like a serious journey. But as we keep on going, education, learning, wisdom is going to come with it. You can't fear it. Well, it's okay to fear it, but you can't run away from it. You got to go through it and just do what you got to do. You feel me? But now that, all the pieces have fallen together in place, let's get started to what we said we were going to do. We are on Chapter 12, Electric Current and Related Variables in Engineering. And we are on Section 2. Voltage is Section 1. Photo emission is Section 1. Alright, here we are. Okay, and just to let y'all know, there's some questions at the end of Section 1, as you can see right there. I'm just going to read them to you and answer them. That way y'all know that the information from the first section has been retained. Alright? In what unit is electric current measured? That is an ampere. Like I always mess the name up. I don't know if I'm saying it right, but if you see AMP, shout out AMP, because that's really smart if they really were thinking about like engineering style things, because that's the current and that's the flow. That's like the poltergeist of what's going on in society. So shout out to Kai Sanat, Agent, Phantom, Duke Dennis, all of them. And I'm only saying the mainstream ones because I'm I don't need to explain myself every single time, but shout out to AMP. They doing their thing, if they really were thinking about it in this way, because that is how electric current is measured. That is the flow of electricity. But anyway, explain what is meant by voltage. Voltage is like pure energy. That's like what electric, like let's say you have 240 voltage. That's the amount of electricity that you have to use in that certain given situation. And then the flow of amp is how much of it's getting pushed through past resistance. Explain what is meant by direct current. Direct current is just flows one way. It doesn't go any other way except forward. Alternating current, or AC, it goes one way, but it can also reverse. It can go back and forth. They have these things called diodes that can transfer an AC into a DC. In your own words, explain how electricity is produced in a conventional power plant. The way it pretty much works is there's all little fractions of, I think the word is parallel arrangement, that work together in, let me see if, I'm gonna make sure I'm saying that right. Yeah, that work in a form of series arrangements. Okay, so the way it goes is this: get coal, you like start bringing it in to get burned. As it's burning, the gas of that gets mixed in with the, like, starts heating up. Wait, hold on. My fault, y'all. I thought I had it and I didn't. It's okay to accept when you fumble the bag. We can re-look at it. But I'm pretty sure how it works is you get coal burning and it makes the water steam up, and the steam of the water gets the turbine going, and the turbine starts going, and it gets these wire that's connected to a magnet moving in, and that causes electricity on a grand scale. That starts the power plant. Whew, I thought I had to like really read it for a second to make sure. I'm gonna read it for a second to make sure, but that's exactly how it worked. Like, I was trying to get like all the technical parts in, but heat up some coal to steam up some water to get the turbine moving, to start moving the wire that's connected to this magnet and make it move so fast that it creates electricity. Did I get that right? It looks like it. Cool. Now they're saying to explain Kirchhoff's law. It's like an equal amount of what's coming in must come out. So like, let's say I have a level of 100 coming in. I need to have a level of 100 coming out. I know I'm not saying that so technical, but I'll share it with y'all in the more technical terms. Give me a second. The law states that at any given time, the sum of the currents entering a node must be equal to the sum of the current leaving the node. Now, I'm not going to hold you. I was a little nervous of saying amp because I wasn't sure if that's what they were saying, but amp and current are literally synonymous. So the same amount of electric current that's coming into a node, a object, must have the same amount of electric current that's leaving it. That is Kirchhoff's law. You feel me? All right. And then we already talked about ampere, direct current, alternate current, and voltage. So that is all the things that they have on the before you go on thing. So we're going to move on. So section 2, electrical circuits and components. And I promise you guys, the more I do this, the better I'm going to get. Like right now, I'm just shaky because I am. Like, the fuck? But anyway, section 2. Electrical circuits and components. An electrical circuit refers to the combination of various electrical components that are connected together. Examples of electrical components include wires, conductors, switches, outlets, resistors, and capacitors. First, let us take a closer look at electrical wires. In a wire, the resistance to electrical current depends on the material from which the wire is made and its length, diameter, and temperature. Materials show varying amounts of resistance to the flow of electric current. Resistivity is a measure of resistance of a piece of material to electric current. The resistivity values are usually measured using samples made of 1 centimeter cube or a cylinder having a diameter of 1 mil and length of 1 feet. The resistance of the sample is then given by R equaling PL, or where P is the resistivity and L is the length of the sample, divided by A, and A is the cross-sectional area of the sample. where P is the resistivity and L is the length of the sample and A is the cross-sectional area of the sample. Okay. The resistance for 1 foot long wire having a diameter of 1 mil made of various materials is given in table 12.1. The electrical resistance of a material varies with temperature. In general, the resistance of conductors, except for carbon, increases with increasing temperature. Some materials exhibit near zero resistance at very low temperatures, temperatures approaching absolute zero. This behavior is commonly referred to as superconductivity. Table 12.1, electrical resistance for 1 feet long wires made of various metals having a diameter of 1 mil at 20 Celsius. There you go, y'all. That is it right there. I know you see it. I know you see it. Alright, on to the next. Next, we are learning about Ohm's law. Ohm's law describes the relationship among voltage, resistance, and current, I, according to V equals RI. So, what are they trying to say? V is voltage, R is resistance, I is current, I is also amp. Current and amp are synonymous. And this formula is voltage equals resistance times current. Note, from Ohm's law equation 12.3, that current is directly proportional to voltage and inversely proportional to resistance. As electrical potential is increased, so is the current. And if the resistance is increased, the current will decrease. The electrical resistance is measured in units of ohms, or like that Greek, that omega symbol. An element with 1 ohm resistance allows a current flow of 1 amp when there exists a potential of 1 volt across the element. Stated another way, when there exists an electrical potential of 1 volt across a conductor with a resistance of 1 ohm, then 1 ampere of electric current will flow through the conductor. Woo! You know what's beautiful? Understanding section 1 makes this so much easier to read. Example 12.1. The electrical resistance of a light bulb is 145 ohms. Determine the value of current flow through the lamp when it's connected to a 120 volt source. Using Ohm's law equation 12.3, we have voltage equals resistance times current. Then you have you do your algebraic equation, and then you get it to current equals voltage divided by resistance, or 120 divided by 145. This equals 0.83 ampere. Let me just show you the example so you guys catch my drift right there. Hold it there for a quick second for y'all to get the vibes. Blessings, blessings, blessings. Alright. Next, we move on to the American wire gauge, or AWG. Electrical wires are typically made of copper or aluminum. The actual size of wires is commonly expressed in terms of gauge numbers. The American wire gauge, AWG, is based on successive gauge numbers having a constant ratio of approximately 1.12 between their diameters. For example, the ratio of the diameter of number 1 AWG wire to number 2 is 1.12. 289 mils divided by 258 mils equals 1.12. Or as another example, the ratio of diameters of number 000 to number 00 is 1.12. 460 mils divided by 410 mils equals 1.12. Before we continue this, I want you guys to see the diagram to really understand what they're trying to say, because a lot of what I'm saying, if you don't get the visual representation, it might confuse you, especially if you're a beginner like myself. So here's the example right here. You see what I'm saying? And what they're describing is the relationship that they all have amongst one another in relation to each other, like ratio wise. As I did with section 1, I'm going to take a couple days to go back through it to understand it, answer the questions. That way, next time you guys see me, I'll have a better understanding of this. You feel what I'm saying? But anyway, I just wanted to give you guys that reference for anyone that is on here and is, having a hard time following. Oh, and I just peeped that someone entered in the chat. I apologize. Let me see. Olivia Ben 256. Hey, how are you? I am doing well. Thank you for joining the chat. I'm doing well. But let's not cap. This also might be someone trying to sell me something. It's kind of hard to like really like engage with the comment section when you're always thinking that someone's going to sell you something. So I'm going to do my best not to assume that Olivia is here to try to sell me on something. But I don't know how long it was since she asked this, but we'll just stay here to like, if she wants to continue to chat, we'll talk with her. For anyone that's on YouTube that sees this, the person that wants to chat is from Twitch. And if you want to follow her page or check her out, oh man, I don't even mean to dox you like that if you don't want to be doxed. Well, fuck you came on my page, so you're getting doxed. Shout out to Olivia Ben 256. Thank you for coming to my page. I hope you learned something today as much as I'm learning. But while I'm waiting for you to respond for that, I'm going to get right back into this. Moreover, the ratio of cross sections of excessive gauge numbers is approximately 1.12 to the power of 2, which equals 1.25. The ratio of the diameters of wires differing by 6 gauge numbers is approximately 2.0. For example, the ratio of diameters of wires number 1 to number 7 is 2. 289 mils divided by 144 mils equals 2. Or the ratio of diameters of number 30 to number 36 is 2. 10 mils to 5 mils, which equals 2. Table 12.2 shows the gauge numbers, the diameters, and the resistance for copper wires. When examining table 12.2, note that the smaller the gauge numbers, the bigger the wire diameter. Also note from data given in table 12.2 that the electric resistance of a wire is increased as its diameter is decreased. The National Electric Code published by the Fire Protection Association contains specific information on the type of wires used for general wiring. The code describes the wire types, maximum operating temperatures, insulating materials, outer cover sheaths, the type usage, and the specific location where a wire should be used. Today, a typical home has a total of 200 ampere rating. You also will find that various types of wires are used for general wiring, ranging the American wire gauge numbers of 0 to 14. You know what's really crazy about that? I was talking to my friend Dunk Dallas, and he was saying it was about like 150 to 300 ampere to charge a house, and I wasn't like to like run through a house, and I was just like, I don't know, but here it is. So shout out to him for making like a great call. Now I'm about to take a picture and let him know. But also I'm thinking about going live on TikTok and also finishing the rest of this out there as well. Even though I'm not able to connect it to OBS, I can still go on it on my phone and then, you know, let it rip. But the only thing is that I don't even have a stand for TikTok. I actually do have a stand, I just don't have it on me. Maybe for another time, because we do got to go. But we might have more time than I think. See if I'm not even like, if I'm to be honest with you. Hold on. Let me see. Did I do what I said I was gonna do? Yes, I sent it. So what's next in this journey? Okay, I showed you guys the table already, but you know, doesn't hurt to show it again. Let me make sure that y'all here. There, give y'all a little second, and then boom. All right, that's good enough. Alrighty, next section: electric power. The electric power consumption of various electrical components can be determined using the following power formula. Power equals wow, I'm having a brain fart. Voltage. I was gonna say velocity, but voltage times current. Power equals voltage times current. where P is power in watts, V is the voltage, and I is the current in amps. The kilowatt hour units are used in measuring the rate of consumption of electricity by homes and businesses. 1 kilowatt hour represents the amount of power consumed during 1 hour by a device that uses 1 kilowatt or 1,000 joules per second. That's nice to know. 1 kilowatt equals 1,000 joules per second. Moving forward, appliances and home electronics power consumption. Let us now turn our attention to the power consumption of typical home appliances and electronic devices. The range of power consumption for common appliances and electronics such as clock radio, coffee maker, clothes washers, clothes dryers, fan, hair dryers, television, toasters, and toaster ovens, and vacuum cleaners are shown in table 12.3. As you can see, hot water heaters, dishwashers, and clothes dryers are among the energy hogs. For example, clothes dryers, depending on their size, could consume between 2,000 to 5,000 watts. So if you run a clothes dryer with a power rating of 5,000 watts for 2 hours, it will consume 5,000 watts times 2 hours, which equals 10,000 watts per hour. 10,000 watts minus H equals 10 kilowatts of energy. Hold on. Okay. So it's like 10,000 watts per hour, or you could just say 10k kilowatts of energy. An example of home electronics. A 46-inch LCD TV could consume about 250 watts. Wait, hold on. That really just threw off my whole momentum. As an example of home electronics, a 46-inch LCD TV could consume about 250 watts. So if you watch this TV for 4 hours, then the TV will consume 250 watts times 4 hours, which equals 1,000 watts per hour, or 1k kilowatt hours. 1k kilowatts per hour of energy. Example 12.3. Let me just show y'all. It's like a cute little picture right there. First of all, let me see if it's even there. Let me go to Streamlabs, could show you even respond. And then you see the pictures. That's cute, whatever. And then that's the formula right there. That way y'all can see it. Let it sit there for a little bit. Alright, back down. I'm just an old lump of coal, but I'm gonna be a diamond someday. I have no idea what that's about. Anyway, example 12.3. Assuming that your electrical power company is charging you 10 cents for each kilowatt I'm gonna say kilowatt hour. I'm saying kilowatt per hour. Hold on, let's start from the beginning. Assuming that your electric power company is charging you 10 cents for each kilowatt per hour usage, estimate the cost of leaving 5 100-watt light bulbs on from 6 p.m. until 11 p.m. every night for 30 nights. Oh. 5 light bulbs, 100. Oh, that's actually a really dope breakdown of it. What I'm trying to make sure of that I'm not tripping about, is it like this full equation, or is this like slowly but surely breaking it down as time goes on? So it says, assuming that your electric power company is charging you 10 cents for each kilowatt hour usage. Okay, so 10 cents per each kilowatt hour. Estimate the cost of leaving 100-watt light bulbs on from 6 p.m. till 11 p.m. What's up, babe? Oh, pizza. When do you think I should go get it? Now-ish?
Oh, you have time. Like,
You think so?
yeah.
Hold on, let me see. I want to see how long it's gonna take me to get to section 3. All right. I'm currently on 410. Damn, chat. It is going to take me a minute to get to section 3. I might have to stop here for now. Give myself some time to think about example 12.3, and then get back to y'all, because when pizza's calling, I must answer. I must answer the call.
It's on the table.
All right, bet. If y'all heard that name, honestly, I don't even feel like I have enough followers for that to even matter. And even if it did matter, you know what I mean? I'm already doxxed. It's not like it's impossible for y'all not to find them. I'm just not a nigga that likes to put my shit out there in public too much. I'm gonna tell y'all about it, obviously, but I'm not trying to put that shit out there, you know? But anyway, I'm gonna go get some pizza. I'm gonna go chill with my fam. I'm gonna eat something. And as always, I wish y'all nothing but wealth, health, happiness, and of course, cheeks. Don't be silly. Wrap your willy. Peace. The reason why I pause is because I feel like there's something else I should say. We will be back with the engineering thing. I feel like I said that already. Yeah, I can't think of it. All right. Peace. I'll holler at y'all niggas later. Let me get that pizza.